More than 1 billion years ago, Earth did not look the way you imagine it. There were continents, there were oceans, there was sunlight, but there were no forests, no animals, no footprints in sand. All of Earth's land was gathered into a single vast supercontinent. Rodinia. It stretched across much of the planet, a continuous expanse of rock and rising mountains, with interiors so far from the sea that climate behaved differently from anything we know today. There were no trees to hold the soil, no roots to slow erosion, no creatures moving across the ground. Most life remained microscopic, drifting in oceans that were still chemically different from our own. The sun shone slightly dimmer than it does now. Days were shorter, oxygen levels were lower. The world was stable, but biologically quiet. It was not the violent chaos of Earth's formation. It was not the green, crowded planet that would come later. It was something in between, a world that appeared complete, yet remained biologically unfinished. Tonight, we travel back to Rodinia, guided by magnetic traces locked inside ancient rock and the slow movement of continents over deep time. But before we begin, I'd love to know where in the world you're listening from and what time it is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's distant past, please do consider leaving a like and subscribing to the channel. So now take a deep breath, let your shoulders loosen, and let's step onto the continent that once held nearly all the land on Earth. Time in geology is less like a line and more like an ocean of depth. Some eras drift near the surface of awareness, familiar and well lit, while others rest far below, suspended in distances so immense they resist intuition. The age of Rodinia lies between roughly 1.1 billion and 0.75 billion years ago, set deep within the Proterozoic Eon. It occupies a middle chapter of Earth's history so remote that even the reign of dinosaurs, once imagined as impossibly ancient, stands far closer to us than this world does. To situate it clearly, one must pass beyond forests and beyond animals, beyond even the first complex bodies that left visible traces in stone. Before Rodinia assembled, Earth had already endured nearly 3 billion years of change. The earliest crust had cooled from molten beginnings. Oceans had gathered from vapor. Microbial life had quietly altered the chemistry of air and sea, releasing oxygen that reacted with dissolved iron and settled into rock. By the time continents converged into a single immense landmass, the planet was no longer young, yet it remained biologically restrained, its surface largely untouched by the intricate ecosystems that would later define it. Rodinia belongs to a stretch of time that often slips from popular imagination because it lacks familiar anchors. There are no towering reptiles, no shells scattered along beaches, no forests thick with shadow. The word prehistoric does not fully capture it. Prehistoric suggests a world before written memory, but still rich with animals whose shapes resemble those alive today. Rodinia predates not only history, but animals themselves. It is pre-animal Earth, a planet shaped more by tectonic forces and microscopic metabolisms than by visible movement. After Rodinia, the story gradually shifts. As this supercontinent began to fragment, new coastlines formed and fresh ocean basins opened. Changes in weathering and circulation influenced atmospheric balance. Over the hundreds of millions of years that followed, oxygen levels rose in subtle increments. Multicellular life diversified in the sea. Eventually, soft-bodied organisms of the Ediacaran period appeared, unlike anything that had come before. Later still, during the Cambrian, marine ecosystems filled with forms that established much of the blueprint for complex life. Before Rodinia, Other supercontinents had assembled and dispersed in slow cycles, reaching back toward Earth's early eons. The planet had practiced this rhythm before, but during Rodinia's tenure, conditions were poised between microbial dominance and the threshold of complexity. It stands neither at the violent beginning nor within the crowded biological world that would follow, but in a prolonged middle movement. The span between 1.1 billion and 0.75 billion years ago is difficult to grasp. Human civilization occupies only a brief shimmer atop the present. Even the entire age of mammals is a narrow slice compared to the gulf separating us from Rodinia. The interval feels abstract because its evidence is subtle. In younger rocks, bones and shells bridge imagination and proof. In this older world, scientists rely more heavily on indirect traces. Isotopic ratios preserved in minerals hint at atmospheric composition. Magnetic orientations locked inside crystals record ancient latitudes. Tiny fossils of microbial mats reveal quiet persistence. This distance in time partly explains why Rodinia remains less known than the age of dinosaurs. The fossil record here whispers rather than displays, yet the era forms an essential layer within the continuous narrative of Earth. Beneath later forests and cities lie rocks shaped during its assembly and fracture. Beneath familiar chapters rests this deeper one, steady and immense, holding its place within the unfolding story of the planet. Beneath the continents, far below soil and stone, the planet moves with a patience that does not match the rhythm of human thought. The surface appears firm and complete, yet it rests upon plates of lithosphere that float atop the warmer ductile mantle. These plates drift not with urgency, but with quiet persistence, driven by heat rising from Earth's interior and by the slow sinking of cooled oceanic crust at distant boundaries. Over spans of tens and hundreds of millions of years, this motion reshapes the arrangement of oceans and land without spectacle. A supercontinent is not a sudden event, but the result of convergence accumulated across immense durations. It forms when most of Earth's continental blocks, once separated by ocean basins, gather into a single connected mass. The process begins subtly. Oceanic crust slides beneath the edges of continents in subduction zones, drawing land masses closer through the steady consumption of seafloor. Island arcs collide with continental margins. Smaller cratons attach along sutures, each impact folding and thickening the crust. Through repetition and time, fragments become assemblies, and assemblies become something larger. During the era that shaped Rodinia, continents that had long wandered independently began to approach one another across shrinking oceans. The closures of these basins were not uniform or symmetrical. Some regions collided obliquely, creating belts of sheared rock and metamorphosed crust. In other areas, head-on collisions compressed sediment layers into vast mountain chains. As buoyant continental crust resisted subduction, it crumpled instead, stacking and uplifting into ranges that once rivaled the greatest heights on Earth, though erosion has since softened their outlines. This gradual assembly reflects a broader pattern in planetary behavior known as the supercontinent cycle. Earth has not built such immense landmasses only once. Over billions of years, continents converge, merge, and later fragment again, only to repeat the process. Heat accumulates beneath the thick continental lithosphere, eventually contributing to rifting and dispersion. The cycle unfolds slowly, guided by mantle convection and the internal energy that has remained active since the planet's formation. In this sense, Rodinia was one expression of a deeper rhythm rather than an isolated anomaly. As continents pressed together, the crust thickened and stabilized into wide interiors, far removed from oceanic influence. Sutures marked the scars of closure, recording where seas had vanished and land had welded to land. Mineral assemblages formed under intense pressure bear witness to these collisions, transformed by temperature and compression into rocks such as gneiss and shear. Zircon crystals crystallized within these environments, later preserving isotopic signatures that allow modern scientists to date the stages of assembly with remarkable precision. The mountains raised during this era influenced more than topography. Elevated regions altered patterns of rainfall and erosion. Exposed rock surfaces underwent weathering, drawing carbon dioxide from the atmosphere through chemical reactions that would subtly affect climate. Sediments carried from highlands accumulated in basins along new coastlines, building thick sequences that now serve as archives of this distant time. Even in their absence, long worn ranges continue to shape the geology of present continents, their cores embedded within modern landscapes. Continental drift operates at rates measured in centimeters per year, yet over hundreds of millions of years, such motion is transformative. What appears static within a human lifetime becomes fluid across geological ages. The making of Rodinia unfolded not in a single dramatic episode, but in overlapping chapters of convergence, uplift, and stabilization. Through the steady collision of plates, Earth gathered much of its land into one immense expanse, setting the stage for climates and environments unlike those of today, all accomplished through movements so gradual that no single moment could reveal their full design. Light would have fallen across land that felt unfinished, not in its structure, but in its texture. The assembled continent stretched outward in broad expanses, and far from its margins the air grew drier, clouds thinning as they crossed long distances without replenishment from nearby seas. In these interiors, precipitation likely arrived sparingly. Without regular moisture, the surface took on the character of desert, though not the desert of dunes shaped by grasses or shrubs. This was a bare expression, where exposed bedrock and loose mineral grains met the wind without obstruction. Soil, as it is known today, had not yet matured into thick, layered complexity. Modern soils owe much to roots that break apart stone and to organisms that churn and enrich the ground. During the time of Rodinia, such activity remained absent on land. Chemical weathering still occurred, but it unfolded slowly and directly upon exposed rock. Rainwater, slightly acidic from dissolved gases in the atmosphere, seeped into fractures and reacted with minerals. Temperature shifts expanded and contracted stone. Over long spans, these processes reduced mountains and plateaus grain by grain, yet the resulting sediment often remained thin and patchy, easily redistributed by wind and sparse runoff. The landscape would have appeared dominated by rock. Vast plains of granite and metamorphic crust extended across the continent's interior, interrupted by the remnants of uplifted belts forged during collision. These highlands, once sharp and angular, began to soften under erosion, though the pace differed from that of vegetated mountains in later ages. Without roots to anchor slopes or organic matter to bind particles together, gravity acted more directly upon loose material. Sheets of debris slid downslope during rare storms, spreading coarse fragments across broad surfaces. Rivers, when they formed, behaved differently as well. In a world without plants to stabilize banks, channels likely shifted frequently, braiding across wide floodplains. Sediment loads may have been heavier during intense rainfall, for nothing held back the flow of eroded particles. Yet the absence of deep soils also meant less organic matter entering streams and fewer biological interactions influencing the chemistry of runoff. The water carried minerals weathered from rock, shaping the composition of shallow basins and coastal margins far away. Color across this surface would have been muted. Without forests or even low vegetation to soften the horizon, expanses of stone reflected sunlight in subdued tones of gray, rust, and pale brown. Iron-bearing minerals oxidized where exposed to air, tinting some regions with red hues. Elsewhere, freshly fractured rock retained cooler shades. Dust lifted by wind may have drifted across the plains, settling again in thin veils. The textures were stark, shaped by physical forces more than by living systems. Biological influence on land remained subtle. Microbial films might have colonized moist niches along coasts or around ephemeral pools, forming delicate mats that stabilized sediment in narrow bands. But across much of the interior, life's imprint stayed faint. There were no burrows to aerate ground, no roots to penetrate cracks, no leaf litter to gather in depressions. The boundary between atmosphere and lithosphere felt direct and unmediated, as though the planet's surface lay closer to its mineral foundations. Erosion patterns reflected this simplicity. Weathering profiles were thinner, slopes more exposed, and sediment transport more episodic. Over millions of years, entire mountain ranges would gradually diminish, their debris spreading outward into lowlands and eventually reaching distant shores. The surface of Rodinia, shaped largely by rock, water, wind, and gravity, carried the marks of a planet still awaiting the intricate transformations that later life on land would bring. There are stretches in Earth's history when the color green had not yet claimed the land. During the age of Rodinia, continents rose and settled beneath the open sky, yet no forests softened their outlines. The surfaces described earlier, sculpted by wind and rain alone, remained untouched by stems or leaves. Life had not extended itself onto soil in any visible abundance. Whatever biological complexity stirred within oceans had not crossed that boundary. Without plants, the ground held a different character. No roots threaded downward to pry apart stone, to widen fractures, or to anchor slopes against gravity. Mechanical weathering still fractured rock, and chemical reactions still altered minerals, but they proceeded without the intricate collaboration that vegetation would later provide. In more recent ages, forests breathe into the earth as much as into the air, sending roots deep into cracks and drawing nutrients upward. Here, that silent labor had not begun. The crust lay closer to its mineral origins, exposed and direct. The absence extended beyond trees. No leaf litter gathered in shallow depressions to form dark layers of humus. No fallen branches accumulated along stream margins. Organic material did not blanket hillsides in seasonal rhythms of growth and decay. The surface cycled through dryness and rainfall without the buffering presence of biomass. Sediments moved unbound by tangled roots or fungal networks, shifting according to slope, storm, and time. Insects had not yet emerged to explore this terrain. No delicate wings caught the light above rocky flats. No burrowing arthropods aerated sediment beneath the surface. Later chapters of Earth's story would fill landscapes with intricate interactions between plants and animals, pollination, decomposition, symbiosis woven into cycles of renewal. On Rodinia, such exchanges remained confined to the sea. The land, in comparison, seemed structurally prepared but ecologically sparse. Birds, too, belonged to a far distant future. Air moved freely across open expanses, unbroken by flocks rising or settling in branches. The sky held clouds and drifting particles, yet it lacked the layered life that would eventually occupy every altitude. Sound on land emerged only from physical forces, from wind crossing uneven ground or from water descending through channels after rain. The delicate tremors of the living movement were largely absent. This ecological restraint carried a subtle weight. Modern continents are shaped as much by biology as by geology. Forests influence rainfall patterns through transpiration. Roots alter the stability of slopes and riverbanks. Organic acids accelerate chemical weathering, and soil organisms transform mineral grains into structured horizons rich with nutrients. Without these influences, Earth's processes on land unfolded in simpler loops. The cycling of carbon and other elements lacked the amplifying pathways that vegetation would later introduce. Color offered another contrast. Today, even from orbit, continents display broad swaths of green, marking photosynthetic activity. In the time of Rodinia, such signals would have been faint or absent across most terrestrial surfaces. Rock, sand, and weathered mineral crust dominated the palette. Along certain coasts, microbial films may have formed thin veneers, hinting at life's persistence, yet these remained localized rather than expansive. The difference was not merely aesthetic. Plants would eventually regulate atmospheric composition through large-scale photosynthesis on land, reinforcing oxygen levels and stabilizing carbon dioxide through burial of organic matter. In their absence, atmospheric balance depended more heavily on oceanic processes and geological feedback. The biosphere had begun transforming the planet, but much of its influence remained seaborne. A planet without forests does not lack structure or grandeur. Mountains still rise, rivers still trace their courses, and light still sweeps across horizon after horizon. Yet the intricate, layered web that green life brings to land had not yet taken hold. The continents of Rodinia stood expansive and exposed, awaiting the long evolution that would one day drape them in living cover. Above the silent continent, the sky carried a character shaped by chemistry as much as by light. Sunlight still crossed space and reached the surface, yet the star that illuminated Rodinia was younger and slightly less luminous than the one that warms the present Earth. Over billions of years, the sun has brightened gradually as hydrogen in its core fuses into helium, increasing energy output with slow inevitability. During this earlier chapter, that output was modestly reduced, altering the balance between incoming radiation and atmospheric response. A dimmer sun did not plunge the planet into darkness, yet it shifted the subtleties of illumination. The angle of light, the intensity of glare on rock and sea, and the gradients between dawn and noon carried differences too gradual for human eyes to measure directly, but meaningful in long-term climate equations. Earth remained habitable, but it existed within a delicate balance often described as the faint young sun paradox, where lower solar brightness was countered by atmospheric conditions capable of retaining warmth. Oxygen levels during the time of Rodinia were lower than those of the modern era. The great oxygenation events of earlier eons had transformed the planet's chemistry, yet atmospheric composition had not reached the concentrations familiar today. With less oxygen present, and with varying levels of carbon dioxide and perhaps trace methane, the scattering of light through the atmosphere likely differed in subtle ways. Modern blue skies arise primarily through Rayleigh scattering, a process in which shorter wavelengths of sunlight are scattered more efficiently by molecules such as nitrogen and oxygen. Changes in atmospheric density and composition adjust how this scattering unfolds. If particulate matter or photochemical reactions introduced fine aerosols into the air, a faint haze may have softened horizons. Volcanic activity associated with tectonic movements could release sulfur compounds and other gases that, upon oxidizing, form tiny droplets suspended high above the ground. Even small variations in such particles influence how sunlight disperses, lending the sky a slightly muted or pale tone compared to the crisp cobalt often seen today. The overall color would still have belonged to the spectrum of blue, yet perhaps less saturated, with gradients that shifted gently toward white or gray under certain conditions. In regions where atmospheric gases interacted with incoming radiation differently, sunrises and sunsets might have displayed hues subtly altered by the proportions of scattering molecules. The interplay between sunlight and air is not static. It is a dynamic equation shaped by concentration, pressure, and the presence of reflective surfaces below. Without dense terrestrial vegetation, fewer biological emissions entered the lower atmosphere from land. In later eras, forests release organic compounds that participate in complex chemical reactions, affecting cloud formation and light diffusion. During Rodinia's tenure, such contributions from land remained minimal. Atmospheric composition leaned more heavily on volcanic outgassing, oceanic exchange, and the slow metabolism of microbial communities. These factors, combined with solar intensity, created a sky that was familiar in structure yet distinct in tone. Cloud formation also depends upon atmospheric chemistry. Water vapor condenses around microscopic nuclei, and the type and abundance of these particles influence cloud brightness and longevity. Variations in aerosols could have altered the appearance of cloud decks, perhaps lending certain regions a gauzy brightness or a diffused glow at particular latitudes. The sky above Rodinia was not alien in shape. It arched, reflected sunlight, and shifted from dawn to dusk as it does now. Yet its color carried the imprint of a different balance of gases and radiation. In that subtle difference lay a reminder that even something as seemingly constant as blue can evolve over deep time, shaped quietly by the chemistry of air and the slow brightening of a star. While the continent gathered itself into vast interiors, water held the larger share of the planet. The oceans spread beyond every horizon, uninterrupted by ships, reefs built by animals, or kelp forests swaying in coastal light. They covered most of Earth's surface, moderating temperature and exchanging gases with the atmosphere in steady cycles. In this era, the sea was not a supporting actor to life on land. It was the primary stage upon which biology unfolded. Within these waters, microbial life flourished with quiet persistence. Cyanobacteria and other microorganisms occupied sunlit layers near the surface, harvesting light through photosynthesis. Their activity had already reshaped the planet in earlier ages, releasing oxygen that reacted with dissolved elements and accumulated gradually in the air. Alongside them lived diverse prokaryotes and early eukaryotic cells, drifting, dividing, and evolving in forms too small to see without magnification. The ocean was not empty of complexity. It simply expressed that complexity at microscopic scales. Chemical conditions in these seas differed in meaningful ways from those of the present. The balance of dissolved gases, nutrients, and trace metals reflected both atmospheric composition and the nature of weathering on land. With continental surfaces largely free of deep-rooted vegetation, the delivery of minerals into coastal waters followed patterns unlike those of later green worlds. Rivers carried ions liberated from rock, influencing salinity and alkalinity. Carbon cycled between water and air through biological uptake and inorganic reactions, adjusting the ocean's chemistry over immense spans. In some regions, particularly in deeper or poorly circulated basins, iron may have remained more soluble than it does in well-oxygenated modern oceans. When oxygen levels were lower, dissolved ferrous iron could persist in water, lending a faint greenish or reddish tint under certain conditions. As photosynthetic microbes released oxygen locally, that iron would oxidize, precipitating as iron oxides that settled into sediment. Banded iron formations from earlier chapters testify to similar processes, though by the time of Rodinia, many oceans were more oxygenated than in Earth's distant youth. Even so, localized chemical gradients likely produced varied marine environments. Life concentrated most densely where sunlight and nutrients converged. Shallow coastal shelves, bathed in light and periodically stirred by tides and currents, formed broad zones of productivity. Microbial mats may have spread across tidal flats, forming layered communities that trapped sediment and built subtle textures across the seafloor. In these marginal waters, early eukaryotes found niches that encouraged experimentation in cell organization and metabolic pathways. The proximity of land allowed nutrient input through runoff, while the sea provided stability against extreme temperature shifts. Farther offshore, deeper waters hosted their own ecosystems shaped by pressure and reduced light. Hydrothermal activity along mid-ocean ridges released mineral-rich fluids, supporting chemosynthetic life independent of sunlight. These vent communities, though likely simpler than modern analogs, demonstrated that energy could flow through pathways other than photosynthesis alone. The ocean, in its vertical dimension, contained multiple worlds layered atop one another. Circulation patterns moved water masses across latitudes, redistributing heat and dissolved substances. Wind stress at the surface drove currents that connected distant basins, while density differences caused by temperature and salinity guided deeper flows. Through these movements, the ocean integrated planetary processes, linking atmosphere, lithosphere, and biosphere in continuous exchange. Though no large animals yet swam through these waters, the sea was not silent in a biological sense. It pulsed with microscopic activity, cell divisions occurring in numbers beyond counting, organic molecules synthesized and recycled in invisible abundance. During Rodinia's tenure, the ocean remained the dominant habitat for life, sustaining and shaping the slow evolutionary steps that would one day extend beyond its shorelines. In this long interval of Earth's history, life did not announce itself with movement large enough to cast a shadow. It persisted in forms measured in micrometers, shaping the planet quietly from within water and along damp margins. The absence of animals did not imply absence of vitality. Instead, vitality operated at scales too small for unassisted sight, in cellular architectures already refined by hundreds of millions of years of evolution. Cyanobacteria remained among the most influential inhabitants of the seas. Through photosynthesis, they captured sunlight and released oxygen as a byproduct, contributing to the gradual enrichment of the atmosphere and upper ocean. Their presence was not isolated. They formed layered communities known as microbial mats, cohesive sheets of cells and sediment bound together by extracellular polymers. These mats spread across shallow marine surfaces, trapping grains, stabilizing substrates, and recording faint ripples of currents in delicate laminae. In tidal zones and sheltered lagoons, such structures accumulated into low domes and columns, subtle biological constructions that left impressions in stone. Within the oceans also lived early eukaryotic cells, organisms whose internal organization differed profoundly from that of simpler prokaryotes. Enclosed nuclei safeguarded genetic material. Membrane-bound organelles carried out specialized functions, increasing efficiency and opening pathways toward greater complexity. These cells likely arose through endosymbiosis, when once independent bacteria became permanent residents within larger hosts, evolving into mitochondria, and, in photosynthetic lineages, chloroplasts. Such unions represented turning points in the architecture of life, though their immediate outward expression remained modest. Complexity advanced gradually. Multicellularity appeared in limited forms among certain algae, where cells adhered and coordinated in loose assemblies. Communication between neighboring cells began to emerge through chemical signaling, allowing differentiation of roles within simple tissues. Yet these developments unfolded over immense stretches of time, without the rapid diversification that would later characterize the Cambrian. Evolution at this stage resembled a slow tightening of threads rather than an explosive branching of branches. Several factors contributed to the delay of animal emergence. Oxygen concentrations, though higher than in Earth's earliest eons, may not have reached levels consistently sufficient to sustain the metabolic demands of larger, mobile organisms. Animals rely on efficient respiration to fuel movement, predation, and internal organization. Fluctuating oxygen levels likely constrained body size and complexity. In addition, ecological relationships required for animal diversification, such as predator-prey dynamics and structured food webs, had not yet fully developed. Genetic innovation also requires time. The regulatory genes that orchestrate body plans, tissues, and developmental pathways had to evolve and stabilize within ancestral lineages. These genetic frameworks did not appear spontaneously. They were assembled gradually through mutation, duplication, and selection. During Rodinia's tenure, these processes advanced silently within microbial and simple eukaryotic populations, laying foundations not yet visible in macroscopic form. Even without animals, interactions within microbial communities could be intricate. Competition for nutrients, symbiosis between species, and viral influences shaped evolutionary trajectories. Horizontal gene transfer allowed advantageous traits to move between lineages, accelerating adaptation in certain contexts. The oceans contain dynamic networks of exchange and transformation, though the participants were minute. Life before animals was neither primitive in a simplistic sense nor static. It was adaptive, responsive, and innovative within its constraints. The sea held a biochemical ferment, and along its illuminated shallows, mats, and films carried forward the incremental refinements of cellular life. Animals had not yet stepped into existence because environmental thresholds, genetic architectures, and ecological scaffolding were still coalescing. In this protracted prelude, the living world rehearsed the elements that would later combine into forms capable of swimming, crawling, and perceiving, even as it continued its quiet dominion at microscopic scale. Across the breadth of the continent, the ground bore no trace of passage. Sand did not compress beneath weight, and mud did not preserve the outline of limbs. Sediment dried in delicate patterns, left only by evaporation and the retreat of water. The surface remained undisturbed by bodies moving with intention across it. What lay under the open sky belonged almost entirely to rock, mineral crust, and the shifting films of moisture that came and went with the weather. Without animals, there were no herds gathering at inland waters, no small creatures threading between stones, no predators scanning horizons for motion. Grazing had not begun because nothing yet grew upon which to graze. Hunting had not emerged because prey did not traverse the plains. The elaborate exchange of pursuit and escape that later defined terrestrial life had not entered the script of this world. Energy captured in oceans remained largely confined there, cycling through microscopic communities instead of flowing into terrestrial food webs. Sound upon land arose from physical forces alone, Wind moved unimpeded across exposed expanses, lifting fine particles and carrying them across slopes. In rare intervals of rainfall, runoff traced temporary channels, and water descended through fractures with muted resonance. Along distant margins where the sea met stone, waves broke rhythmically, their cadence set by tides and wind rather than by biological chorus. The air did not carry calls, wing beats, or the layered hum of insects. The planet spoke in geology. In the absence of burrowing or rooting organisms, the ground lacked the constant turnover that characterizes later soils. Sediment surfaces could remain undisturbed for long spans, interrupted only by episodic events such as storms or landslides. Microbial films might have formed in sheltered depressions after rain, but these were thin and transient, not the architects of complex terrestrial ecosystems. The land existed in a state that might be described as structurally prepared, yet biologically sparse, its potential unrealized. Ecosystems depend upon interaction, and on land, these interactions require actors. Nutrients released from rock did not immediately enter intricate networks of plants and animals. Instead, they accumulated or were transported directly into marine basins. The recycling loops that later knit continents into dynamic systems had not yet taken shape. There were no decomposers breaking down fallen leaves, no pollinators linking flower to flower, no territorial patterns inscribed across landscapes. The threads that would eventually weave land into a living tapestry were still forming in distant environments. This absence altered more than sound and motion. It influenced the very structure of sedimentary layers. In younger strata, trace fossils record the tunnels and trails of organisms, preserving their passage through soft ground. In the time of Rodinia, such bioturbation had not yet reworked surface layers. Sediments could accumulate in clearer, more stratified sequences, unbroken by the churn of digging limbs. The record of deposition, therefore, retained a different character, a quieter arrangement reflecting limited disturbance. Even the chemistry of near-surface environments bore the imprint of restraint. Without extensive vegetation drawing carbon dioxide from the air and releasing organic compounds, atmospheric exchange over land followed simpler pathways. Soil respiration, as it is known today, has not become a dominant process. Instead, interactions between air, water, and mineral surfaces governed fluxes of gases. The balance between lithosphere and atmosphere remained more direct. Silence, in this context, was not emptiness, but incompleteness. The land possessed mountains, plains, and coasts, yet it lacked the intricate web of relationships that would later animate them. The stage stood illuminated, shaped by tectonics and weather, awaiting the arrival of organisms capable of inhabiting its expanse. In that prolonged stillness, Earth held within itself the latent possibility of footsteps that had not yet been taken. Far from the encircling seas, the heart of the supercontinent settled into a climate governed by distance. Moisture carried inland from coastal margins diminished as air masses released their rainfall along mountain fronts and elevated terrain. By the time these currents reached the deep interior, much of their vapor had already fallen away. What remained drifted across vast plains with limited capacity to replenish the land below. In such settings, aridity became less an event and more a prevailing condition. Continental interiors on a unified landmass behave differently from smaller, fragmented continents. When land stretches unbroken across thousands of kilometers, marine influence cannot easily moderate temperature or humidity. Oceans act as thermal reservoirs, absorbing heat slowly and releasing it gradually. In their absence, Seasonal and even daily shifts in temperature can become more pronounced. During Rodinia's tenure, the immense breadth of connected crust likely fostered regions where summers grew intensely warm under prolonged sunlight, while cooler intervals brought sharp drops in temperature once the sun's energy waned. Without widespread vegetation to anchor soil or recycle moisture through transpiration, the hydrological cycle over land operated in a simpler pattern. Evaporation from sparse surface waters returned limited vapor to the atmosphere locally. Precipitation events may have been episodic, associated with passing storm systems or rare incursions of moist air from distant coasts. Between such events, dry winds could sweep across open expanses, redistributing fine sediments and accentuating the starkness of exposed terrain. These conditions find loose parallels in modern central deserts, such as those occupying the interiors of large continents today. Regions like the Sahara or the Gobi illustrate how distance from oceanic moisture, combined with atmospheric circulation patterns, fosters dryness and significant temperature variability. During the age of Rodinia, similar mechanisms would have operated, though within a planetary configuration unfamiliar to present geography. The scale of the unified landmass amplified these effects, extending interior climates across distances exceeding those of many contemporary deserts. Mountain ranges formed during continental assembly would have further shaped atmospheric circulation. As moist air encountered elevated topography, it rose, cooled, and released precipitation along windward slopes. Beyond these barriers, descending air warmed and dried, creating rain shadow zones that intensified interior aridity. Over immense periods, such dynamics sculpted gradients of moisture across the supercontinent, with coastal fringes, perhaps receiving more consistent rainfall, while central plateaus and basins remained comparatively desiccated. Temperature extremes likely reflected the same absence of moderating influence. Daytime heating over rock-dominated landscapes could raise surface temperatures significantly, especially under clearer skies associated with dry air masses. At night, heat radiated back into space with little atmospheric moisture to retain it, allowing rapid cooling. The resulting swings did not require dramatic storms or violent weather, only the steady physics of radiation and heat capacity operating across wide, unobstructed land. Seasonal shifts in Earth's axial tilt would still have produced cycles of longer and shorter daylight at various latitudes. On a supercontinent, however, the response to these shifts could be intensified inland. Without nearby seas to buffer temperature changes, regions deep within Rodinia might have experienced pronounced seasonal contrasts. Sedimentary records from comparable ancient settings suggest episodic deposition tied to fluctuating climatic conditions, preserving clues to patterns of wet and dry intervals across geological time. Such an interior climate shaped not only surface appearance, but also chemical processes. Weathering rates depend upon temperature and moisture. Extended dryness slows certain reactions, while episodic rainfall can produce pulses of erosion. These rhythms influence the delivery of sediments and dissolved minerals to distant basins, linking interior climates to coastal and marine environments. In the center of this immense continent, climate expresses the logic of geography and physics without interruption by extensive terrestrial life. Distance defined moisture, landmass defined variability, and the atmosphere responded accordingly, tracing broad patterns across a world whose scale magnified every gradient. Stillness at the surface did not mean calm below. Beneath the broad sweep of joined continents, the mantle continued its patient circulation, transferring heat from Earth's deep interior toward the crust. Rock at those depths did not behave like brittle stone, but more like a very slow moving fluid, rising where warmed and sinking where cooled. This circulation, known as mantle convection, had operated for billions of years, long before Rodinia gathered its fragments into one mass. Its persistence ensured that no supercontinent could remain entirely secure. When vast stretches of buoyant continental crust assemble into a single block, they act almost like an insulating blanket. Heat escaping from the planet's interior struggles to pass efficiently through the thickened lithosphere. Over tens of millions of years, thermal energy accumulates beneath such an expanse. The lower lithosphere warms, becomes more buoyant, and may begin to thin. Subtle swelling of the surface can follow, not as a dramatic upheaval, but as a gradual uplift across broad regions. Mantle plumes, localized upwellings of especially hot material rising from deeper layers, may also contribute to this restlessness. Where these plumes impinge upon the base of the lithosphere, they transfer additional heat and weaken the crust from below. The rock responds not with immediate rupture but with slow adjustments. Stresses accumulate as the rigid plates resist deformation, storing energy within fault zones and fracture networks that have yet to fully open. Tectonic stability is therefore a matter of balance rather than permanence. Even as mountain belts eroded and interior climates settled into arid patterns, the foundation beneath Rodinia shifted incrementally. Convection currents continued to rearrange forces at plate boundaries and within the supercontinent itself. Zones that had once been sites of collision could later become lines of weakness, predisposed to future separation. The earliest stages of rifting often begin with subtle extension. The crust stretches slightly, thinning over wide areas. Normal faults form as blocks of rock drop relative to their neighbors, creating elongated basins that may fill with sediment or volcanic material. Magma generated by decompression of upwelling mantle can intrude into these fractures as dikes and sills, marking the incipient pathways of new plate boundaries. Such features do not yet constitute an ocean, but they signal a transition from compression to tension. This transformation unfolds gradually. A supercontinent may persist for hundreds of millions of years, while internal stresses quietly reorganize. The process resembles a long exhalation following an earlier inhalation of convergence. As subduction zones consume oceanic crust around the margins, new zones of weakness form within the interior. Over time, extension may localize along particular corridors, where repeated stretching and magmatism thin the lithosphere enough to permit eventual breakup. Geophysical evidence, preserved in ancient rock sequences, hints at these beginnings. Rift-related volcanic deposits, thick accumulations of coarse sediments, and patterns of faulting recorded in crystalline basement all testify to phases when Rodinia's unity began to waver. These traces suggest that even during periods of apparent geological consolidation, forces beneath the surface were preparing the next rearrangement. Earth's tectonic system operates through cycles of assembly and fragmentation, driven by heat and gravity acting over immense spans. Rodinia's formation marked one crest in that cycle, but the same energy that drew continents together continued to operate afterward. Beneath the continent's broad plateau, mantle convection maintained its circulation, redistributing thermal energy and adjusting stresses within the crust. Thus, even at its greatest extent, Rodinia was never entirely fixed. The solidity perceived at the surface masked an ongoing negotiation between buoyant crust and restless mantle. In that negotiation lay the quiet beginnings of future oceans, traced first, not in sudden rupture, but in the slow stretching of stone. Where continents pressed against one another, the crust did not slide smoothly into place. It thickened, folded, and rose. Layers of sediment that had once rested beneath shallow seas were compressed and lifted skyward, transformed by heat and pressure into crystalline rock. Granite intrusions crystallized deep below the surface, while above, immense belts of mountains took shape along sutures that marked the closure of vanished oceans. During Rodinia's assembly, these orogenic zones stretched for thousands of kilometers, forming ranges whose original elevations likely rivaled the highest peaks known in later eras. These mountains were not merely ridges, but vast systems of uplift. As continental blocks converged, buoyant crust resisted subduction and instead stacked upon itself. Thrust faults carried slabs of rock tens of kilometers over neighboring layers, creating thickened roots beneath the visible summits. Isostasy, the gravitational balance between crust and mantle, allowed these thick roots to support elevated topography. In time, erosion would carve valleys and expose deep-seated rocks, revealing the anatomy of collision long after surface forms had changed. Today, the direct outlines of those ranges are gone. The peaks have been reduced, their sharp ridgelines softened by hundreds of millions of years of weathering and tectonic overprinting. Yet their cores persist within ancient cratons and metamorphic belts scattered across modern continents. Minerals formed under extreme pressures record the depths at which they crystallized, offering quiet testimony to mountain heights that no longer stand. What remains are fragments, worn and reassembled through successive cycles, the bones of former giants embedded within newer landscapes. While they stood tall, these ranges influenced more than horizon lines. Mountains alter atmospheric circulation by forcing air to rise, cool, and shed moisture. Windward slopes receive enhanced precipitation, while leeward regions lie in relative dryness. Such patterns would have shaped rainfall distribution across Rodinia, contributing to gradients of vegetation that would one day emerge, though at this time the influence was felt primarily in the movement of water and sediment. Orographic lifting and rain shadow effects structured climates on regional scales, guiding the flow of rivers and the deposition of sediments downstream. Elevated terrain also accelerates weathering processes. Freshly exposed rock reacts with carbon dioxide dissolved in rainwater through chemical weathering, forming bicarbonate ions that are transported to the oceans. There, carbon can be locked into carbonate minerals and eventually buried within marine sediments. This sequence links mountain uplift to the long-term carbon cycle, drawing down atmospheric carbon dioxide and potentially influencing global temperatures. During periods of significant orogeny, enhanced weathering may contribute to climatic cooling over geological timescales. Physical weathering works in tandem with chemical reactions. Freeze-thaw cycles in colder elevations fracture rock mechanically, while gravity drives landslides that deliver debris to lower slopes. Streams incise valleys, carving through uplifted strata and carrying sediments outward toward coastal basins. These erosional processes not only reshape topography, but also regulate the flux of nutrients and dissolved elements to marine environments, integrating mountain systems into broader planetary cycles. The mountain belts of Rodinia therefore functioned as engines of transformation. Born from continental collision, sustained by isostatic balance, and eventually subdued by erosion, they mediated exchanges between atmosphere, lithosphere, and hydrosphere. Though their summits no longer pierce the sky, their legacy endures in altered rock chemistry, in sedimentary archives, and in the global carbon pathways that helped maintain a habitable planet. In their rise and gradual diminishment, they exemplify the quiet dynamism of a world that appears stable yet continually reshapes itself through the interplay of uplift and decay. Above the broad landmass and encircling seas, time itself moved with a slightly different rhythm. The rotation of Earth, steady and unbroken, carried the planet through cycles of light and darkness that were shorter than those experienced today. During the era of Rodinia, a single rotation on its axis required less time, trimming hours from what would later become the familiar length of a day. Sunrise followed sunset with greater frequency, and the arc of light across the sky traced a quicker path from horizon to horizon. This difference was not the result of atmospheric change or continental arrangement, but of celestial mechanics. Earth's spin has been gradually slowing for billions of years, influenced primarily by tidal interactions with the Moon. As our satellite orbits, its gravitational pull raises tidal bulges in Earth's oceans and, to a lesser extent, within the solid crust. Because Earth rotates faster than the Moon revolves around it, these bulges are carried slightly ahead of the line, connecting the two bodies. Gravitational forces between the displaced bulges and the Moon create a torque that transfers angular momentum outward, causing Earth's rotation to decelerate while the Moon slowly drifts farther away. This exchange operates invisibly, yet persistently. The rate of change is subtle on human timescales, amounting to fractions of a second added to a day over centuries. Across hundreds of millions of years, however, the accumulation becomes measurable. Geological evidence, preserved in rhythmic sedimentary layers, suggests that long ago, more days fit within a single year. Tidal deposits and growth patterns in certain ancient minerals record cycles linked to daily and monthly rhythms, allowing scientists to reconstruct rotation rates in deep time with increasing precision. During Rodinia's tenure, the length of a day may have been several hours shorter than the present 24-hour cycle. The difference did not alter the fundamental alternation of light and darkness, but it influenced atmospheric circulation and ocean dynamics. A faster rotating planet experiences a slightly stronger Coriolis effect, shaping wind patterns and the behavior of currents. Subtle adjustments in the distribution of heat and momentum followed, integrating planetary spin into the fabric of climate. Shorter days also implied more frequent transitions between heating and cooling at the surface. Each interval of sunlight delivered energy over a briefer period before giving way to night, while oceans and thick rock moderated extreme temperature swings, especially on large scales. The cadence of heating and radiative loss operated within this adjusted rhythm. The planet's biological and physical systems adapted to it seamlessly, having evolved within whatever temporal framework prevailed. The Moon's gradual recession from Earth continues today, measured by laser-ranging experiments that detect its increasing distance by centimeters each year. This outward drift mirrors the ongoing lengthening of the day, a reminder that celestial bodies remain dynamically connected. In the time of Rodinia, the Moon would have appeared marginally larger in the sky, though the change would be imperceptible without careful measurement. Its gravitational influence, however, left unmistakable signatures in tidal cycles and rotational pace. Rotation defines the boundary between day and night, between warmth and cooling, between illumination and shadow. During this ancient chapter, that boundary turned with slightly greater haste. The difference was modest in the span of a single cycle, yet significant across epochs. Earth's spin, shaped by its partnership with the Moon, carried Rodinia beneath the sun in a rhythm subtly distinct from our own. marking another way in which the planet of that age resembled the present while remaining quietly altered. Carbon moves quietly through Earth, invisible yet persistent, linking stone, air, water, and life in a circuit that never fully stops. During the time of Rodinia, this circuit followed pathways familiar in principle yet different in detail from those of the present. The balance between atmospheric carbon dioxide and long-term storage in rock operated through interactions shaped by tectonics, chemistry, and the absence of widespread terrestrial vegetation. When rain falls upon exposed rock, carbon dioxide dissolved in water forms a weak carbonic acid. This solution reacts with minerals and silicate rocks, breaking chemical bonds and releasing ions such as calcium and magnesium into rivers. Carried to the ocean, these ions combine with carbonate to form solid minerals that settle into marine sediments. Over millions of years, this process removes carbon dioxide from the atmosphere and locks it within limestone and related deposits. Uplifted mountains, as described earlier, enhance this weathering by exposing fresh rock to rainfall, strengthening the drawdown mechanism. In a world without forests, however, the tempo of this exchange shifts. Modern plants accelerate chemical weathering by sending roots deep into fractures, releasing organic acids, and increasing soil moisture retention. They also capture carbon directly from the atmosphere through photosynthesis, storing it in wood, leaves, and soils. During Rodinia's era, these terrestrial contributions were absent. Land surfaces remained largely free of root networks and thick organic layers, meaning that carbon storage within soils was minimal compared to later epochs. The removal of atmospheric carbon dioxide relied more heavily on inorganic weathering and marine biological activity. Volcanic outgassing formed the counterbalance to weathering. Along rift zones and subduction boundaries, magma rising from the mantle released carbon dioxide and other gases into the atmosphere. Large igneous provinces associated with tectonic transitions could inject substantial volumes over extended periods. This input replenished carbon removed by weathering and burial, preventing the atmosphere from becoming permanently depleted. The interplay between these processes created a dynamic equilibrium, fluctuating over geological timescales. Oceans played a central role in mediating these exchanges. Dissolved carbon moves between water and air depending on temperature, circulation, and biological uptake. Microorganisms at the surface incorporated carbon into organic matter, some of which sank into deeper waters and sediments. Burial of this material represented another long-term sink, gradually raising atmospheric oxygen as organic carbon became isolated from oxidation. Though terrestrial plants had not yet joined this cycle, marine life already contributed to its complexity. Feedback mechanisms emerged from the coupling of weathering and climate. Elevated carbon dioxide levels tend to warm the planet by enhancing the greenhouse effect. Warmer temperatures increase rates of chemical weathering and precipitation in some regions, accelerating carbon removal from the atmosphere. As carbon dioxide declines, cooling follows, slowing weathering and allowing volcanic emissions to rebuild atmospheric concentrations. This negative feedback operates like a planetary thermostat, moderating extreme shifts over extended intervals. During Rodinia's tenure, such feedback functioned within the constraints of its geography and biology. Extensive mountain belts provided surfaces for weathering, while the absence of forests limited certain pathways of carbon sequestration. Volcanic activity tied to tectonic restlessness continued to supply gases from Earth's interior. The carbon cycle therefore maintained a balance distinct from that of later green continents, yet effective in sustaining surface conditions, capable of supporting life. Though invisible to the eye, these exchanges shaped climate and ocean chemistry across millions of years. Carbon, moving through rock and water without haste, bound together the geologic and biologic realms. In the time before forests and animals, this quieter configuration of the cycle helped stabilize a planet poised between simplicity and the unfolding complexity yet to come. In certain ancient rocks, faint signatures remain that speak of cold spreading far beyond what later ages would expect. Layers of sediment, once deposited by flowing water, show scratches and angular fragments that suggest transport by ice. Dropstones, isolated pebbles embedded within fine-grained marine deposits, appear where melting ice releases debris into quiet seas. These traces, subtle yet persistent, indicate that during and after Rodinia's assembly, parts of the planet experienced significant glaciation. Glacial deposits from this time are found on multiple continents that were once joined, and paleomagnetic data place some of these sediments at latitudes far from the poles. When rocks preserving evidence of ice also record formation near the equator, the implication is profound. It suggests that cold may have extended into regions that today remain warm year-round. The first hints of such global chill emerge in sequences associated with Rodinia's later history, though precise timing and extent remain subjects of ongoing study. Supercontinents influence climate not only through geography but through chemistry. As mountain belts rise during continental collision, vast expanses of fresh rock are exposed to rainfall and atmospheric gases. Chemical weathering accelerates under such conditions, drawing carbon dioxide from the atmosphere through the reactions described earlier. With no extensive forests to mediate this process on land, inorganic weathering becomes an even more significant pathway for carbon removal. If uplift and exposure are widespread, the cumulative effect can lower atmospheric carbon dioxide concentrations over millions of years. Carbon dioxide acts as a greenhouse gas, trapping heat within the lower atmosphere. As its concentration decreases, the planet's capacity to retain warmth diminishes. Even modest reductions, sustained over geological timescales, can encourage gradual cooling. In a world where solar luminosity was slightly lower than today, the climate system may have been particularly sensitive to such shifts. Reduced greenhouse forcing could tip regional climates toward colder states, allowing seasonal snow and ice to persist longer each year. Geography amplifies these tendencies. A large supercontinent alters patterns of ocean circulation and atmospheric flow, potentially restricting the redistribution of heat from equatorial regions toward higher latitudes. If continental positions disrupt warm currents or enhance the formation of reflective surfaces, feedback may intensify. Ice itself reflects sunlight more efficiently than rock or water, increasing planetary albedo. As ice expands, it reflects more solar radiation, promoting further cooling in a self-reinforcing cycle. Geological evidence suggests that ice sheets advanced into latitudes that had previously remained temperate. Sedimentary sequences preserve striations carved into bedrock by moving glaciers and deposits that resemble modern till. In some cases, glacial layers are directly overlain by marine sediments, indicating a rapid transition from ice-covered terrain to open water, a pattern consistent with episodic glaciation followed by melting. These records hint at dramatic oscillations between cold and milder intervals. Such episodes may represent the early stages of more severe global glaciations that would follow in later Proterozoic times. The climate system, responding to tectonic uplift, weathering rates, volcanic outgassing, and solar input, oscillated within a narrow band. When carbon dioxide drawdown outpaced volcanic replenishment, temperatures declined. When volcanic activity increased or weathering slowed, greenhouse gases accumulated, restoring warmth. Within this balance, ice could advance toward lower latitudes and then retreat again. The first hints of global ice during Rodinia's age therefore arise not as isolated anomalies but as consequences of intertwined processes. Tectonic assembly exposed fresh rock, weathering reduced atmospheric carbon dioxide, cooling encouraged ice formation, reflective surfaces reinforced temperature decline. In ancient stone, these interactions are recorded as quiet markers of a planet testing the boundaries of its own stability, approaching cold expanses that would shape its subsequent chapters. In certain intervals near the close of Rodinia's dominance, the planet approached thresholds that would test the resilience of its climate system. Geological records from the late Proterozoic describe glacial deposits that extend across continents once situated near equatorial latitudes. These findings have led some scientists to propose that Earth may have entered phases of extreme glaciation, periods when ice expanded far beyond polar confines and approached a nearly global embrace. The mechanism behind such severity lies in the reflective nature of ice itself. Fresh snow and glacial surfaces return a significant portion of incoming sunlight back into space, a property known as high albedo. When ice advances across oceans and land, the planet's average reflectivity increases. Less solar energy is absorbed at the surface, and temperatures decline further. Cooling then allows additional ice to form and persist, reinforcing the initial shift. This positive feedback, simple in principle, can become powerful once initiated. During Rodinia's era, several conditions may have aligned to push climate toward this precipice. Enhanced weathering of uplifted terrains could have reduced atmospheric carbon dioxide, diminishing greenhouse warming. At the same time, the arrangement of continents may have influenced ocean circulation, altering the distribution of heat between latitudes. If cooling reached a tipping point where ice sheets began to spread into lower latitudes, albedo feedback would intensify the descent. Marine sediments from later stages of this period include layers, interpreted as glacial in origin, overlain by carbonate deposits that formed rapidly after deglaciation. This juxtaposition suggests transitions from cold, ice-influenced conditions to warmer intervals marked by increased carbon dioxide levels. The rapid accumulation of cap carbonates above glacial strata has been interpreted as evidence that greenhouse gases built up while ice covered much of the surface, eventually driving a swift and dramatic thaw. Whether the planet became entirely icebound remains debated. Some models envision a hard snowball state in which oceans were sealed beneath thick ice from pole to pole. Others propose a slush ball scenario, where equatorial regions retain limited open water. In either case, the climate system would have been operating near its extremes. Volcanic outgassing continuing beneath a frozen surface would gradually increase atmospheric carbon dioxide, since weathering would be suppressed under ice cover. Over time, greenhouse forcing could overpower reflectivity, initiating melting and retreat. Approaching such conditions would have profound implications for ocean chemistry and biological communities. Extensive ice cover would limit exchange between atmosphere and ocean, alter light penetration into surface waters, and influence circulation patterns. Yet evidence suggests that life endured through these intervals, perhaps within refugia such as thin equatorial ice or beneath the surface in hydrothermal environments. The edge of snowball conditions represents a moment when feedback loops briefly outpaced stabilizing forces. Ice amplifying cooling, weathering reducing greenhouse gases, and continental configurations modulating circulation all converged within a narrow climatic corridor. Earth did not remain frozen indefinitely. The same processes that drew it toward widespread glaciation also contained pathways for reversal through volcanic emissions and the eventual breakdown of ice sheets. In this balance between reflection and absorption, between cooling and warming, the planet hovered near a state far colder than any experienced in the age of forests or animals. The possibility that Earth nearly froze over during Rodinia's decline adds another layer to the portrait of a world both familiar in structure and profoundly different in climate, shaped by feedback capable of amplifying small shifts into sweeping transformations. When ice advances across continents and seas, it seems to close the surface to motion, sealing water beneath a hardened shell. Yet even in prolonged cold, the living world does not simply vanish. It adjusts, withdraws, and persists in pockets where energy continues to flow. During the glacial intervals associated with Rodinia's decline, life faced conditions far harsher than those of the arid interiors or temperate coasts that had preceded them. Still, microbial communities endured. Beneath ice-covered oceans, darkness would have expanded as thick layers limited sunlight. In regions where sea ice remained extensive, photosynthetic organisms near the surface may have declined or retreated to thinner margins. Yet the ocean is layered, and not all energy within it depends upon the sun. Along mid-ocean ridges and tectonic fractures, hydrothermal vents released mineral-rich fluids, heated by magma below. These environments provided chemical energy capable of sustaining chemosynthetic microorganisms. Such life derives power not from light, but from redox reactions involving hydrogen, sulfur, and iron compounds. In these vent systems, warmth and chemistry combine to create stable refuges, even as surface waters chilled. Equatorial regions may have retained intermittent or persistent melt zones, areas where sunlight and ocean circulation kept ice thinner or seasonally broken. Even if ice sheets approached low latitudes, complete uniformity across the globe is uncertain. Thin expanses of open water would allow limited photosynthesis to continue, preserving a supply of organic matter that could circulate through marine ecosystems. Microbial mats and planktonic populations adapted to low light conditions may have occupied these niches, adjusting metabolic rates to survive under reduced illumination. Life under ice also depends upon the chemistry of the water column. During extended glaciation, reduced exchange between atmosphere and ocean can alter concentrations of oxygen and other gases. Stratification may intensify, with surface waters isolated from deeper layers. In such settings, microorganisms capable of anaerobic metabolism find opportunities. Sulfate-reducing bacteria and methanogens can thrive in environments deprived of oxygen, continuing biogeochemical cycles in altered form. The diversity of metabolic strategies among early microbes provided resilience against environmental change. Ice itself can shelter life in unexpected ways. Beneath glaciers on land, liquid water can persist where geothermal heat from below melts basal layers. Subglacial lakes and thin films of water along rock surfaces create habitats insulated from external extremes. Although direct evidence from Rodinia's time remains indirect, modern analogs in Antarctica demonstrate that microbial communities inhabit similar environments today. It is plausible that ancient counterparts survived incomparable refugia. Glaciation imposes constraint, but it also shapes evolution. Populations isolated within pockets of habitable space may diverge genetically, adapting to low temperature, limited nutrients, and fluctuating chemical conditions. When ice retreats, these lineages can expand into newly available habitats. The geological record suggests that following severe glaciations, biological innovation accelerated, perhaps reflecting both environmental stress and opportunity. The persistence of life during these intervals underscores a deeper principle. Earth's biosphere had already endured fluctuations in oxygen, temperature, and ocean chemistry long before animals appeared. Its foundations were built upon organisms capable of metabolic flexibility. Even when much of the planet approached frozen conditions, energy sources remained scattered across ocean depths and geothermal zones. Under a canopy of ice that dimmed the surface, microbial life continued its quiet cycles of growth and decay. The resilience of these early communities ensured continuity through climatic extremes, carrying forward genetic and biochemical pathways that would later support more complex forms. In the cold shadow of advancing glaciers, life held its ground, sustained by chemistry, heat, and the enduring capacity to adapt. Even the most unified landmass carries within it the seeds of separation. As heat accumulated beneath Rodinia's thickened crust, the balance that once favored convergence began to shift toward extension. The lithosphere, stretched gradually by forces rising from below, responded not with immediate rupture, but with subtle thinning across broad zones. Over immense spans of time, these regions of weakness lengthened and deepened, marking the earliest stages of continental rifting. Rifting begins as tension pulls opposing sides of the crust apart. Large blocks of rock slide downward along normal faults, creating elongated valleys known as grabens. Between uplifted shoulders, basins form that may collect sediments eroded from nearby highlands. In Rodinia's interior, where collision had once welded continents together, such rifts traced new pathways through ancient sutures. The scars of assembly became corridors of fragmentation. As the lithosphere thinned, decompression within the underlying mantle promoted partial melting. Magma generated in these zones exploited fractures, intruding as vertical sheets and horizontal layers within the crust. In some regions, this process intensified into extensive volcanic activity. Lava poured onto the surface, spreading in broad flows that hardened into dark basaltic plains. These volcanic provinces, vast in scale, recorded pulses of thermal energy rising from deep within the planet. The formation of new ocean basins required more than isolated faults and lava fields. Continued extension eventually allowed the crust to fracture completely, creating a narrow seaway between separating continental blocks. As divergence progressed, basaltic magma solidified to form new oceanic crust along a central spreading ridge. What had once been continuous land transformed gradually into two receding margins, each edged by shallow marine environments. Over millions of years, these embryonic seas widened into full ocean basins, carrying fragments of Rodinia apart. Such fragmentation was not chaotic, but cyclical. Supercontinents assemble through convergence and disassemble through extension, driven by the same mantle convection that fuels plate motion. Thick continental lithosphere traps heat beneath it, encouraging uplift and weakening from below. As rifting initiates, new plate boundaries reorganize the global pattern of subduction and spreading. The planetary engine continues its circulation, redistributing continents across the surface without haste. Volcanism accompanying breakup also influenced atmospheric composition and climate. Carbon dioxide released from magma entered the air, adding to greenhouse gases previously drawn down by enhanced weathering. Large igneous provinces could emit substantial volumes over prolonged intervals, subtly warming the climate and counteracting earlier cooling trends. In this way, tectonic fragmentation participated in the same feedback loops that governed glaciation and deglaciation, linking crustal movement with atmospheric balance. New coastlines formed as oceans expanded. Margins once deep within the supercontinent's interior found themselves bordering warm, shallow seas. Sedimentation patterns shifted accordingly, with marine deposits accumulating along freshly created shelves. Nutrients delivered from eroding uplands entered these basins, stimulating biological productivity in coastal waters. The breakup reshaped not only geography, but also ecological opportunity. Rocks that crystallized during this period preserve magnetic orientations aligned with Earth's field at the time of cooling, allowing later reconstruction of drifting continental fragments. Through these records, scientists trace the gradual dispersal of Rodinia into separate blocks that would continue evolving through subsequent chapters of geological time. The breakup of a supercontinent unfolds slowly, measured in millions of years rather than moments. Faults lengthen, magma intrudes, seas widen, and land masses retreat from one another in deliberate motion. Rodinia, once unified across vast horizons, entered this phase of reconfiguration under the influence of forces that never truly rest. In its fragmentation lay the continuation of Earth's tectonic rhythm, a cycle of gathering and dispersal that reshapes the face of the planet while maintaining the continuity of its deeper pulse. As continents slowly withdrew from one another, the geometry of the planet began to soften. Long interior valleys widened, and water found entry where once there had been only rock. Narrow rifts deepened into seaways, and the edges of separating land masses settled into broad, shallow shelves. These newly formed epicontinental seas did not resemble the vast open oceans beyond them. They were warmer, lighter filled, and in constant dialogue with the land. Shallow water changes everything. Sunlight penetrates easily to the seafloor, enabling photosynthetic organisms to thrive across wide areas. Sediments transported from adjacent uplands spread out in thin layers, providing substrate for microbial communities. The coastline, once a single continuous boundary around a unified landmass, fragmented into a mosaic of embayments, lagoons, tidal flats, and gently sloping continental margins. With increased perimeter came increased exchange, and with exchange came opportunity. Erosion from uplifted terrains fed these developing seas with a steady supply of dissolved minerals and fine particles. Rivers, shaped by earlier tectonic rearrangements, carried ions liberated through chemical weathering into coastal basins. Phosphorus and other nutrients essential for biological growth accumulated in nearshore waters, stimulating primary productivity. Even modest increases in nutrient availability can alter marine ecosystems, favoring certain microorganisms over others and encouraging diversification within planktonic populations. The interplay between land and sea became more intimate as coastlines multiplied. In earlier stages, when Rodinia stood consolidated and interiors lay distant from marine influence, nutrient delivery may have been more localized. Now, as fragmentation progressed, runoff reached new margins from multiple directions. Shallow shelves acted as expansive incubators where chemical gradients, temperature variations, and sunlight created a patchwork of microhabitats. Life, still largely microscopic, encountered environments more varied than those of the earlier unified supercontinent. Marine circulation patterns adjusted in response to newly opened gateways. Water exchanged between basins, altering salinity and oxygenation. In confined seas, restricted flow could lead to stratification, with surface layers differing chemically from deeper waters. Elsewhere, tidal forces mixed sediments and redistributed nutrients across wide areas. Each variation in depth or connection introduced subtle shifts in ecological structure. Such environmental complexity provided a stage for evolutionary experimentation. Early eukaryotes, already present in the oceans, found expanded niches along continental margins. Multicellular algae may have diversified in shallow settings where light was abundant and sediments stable. Microbial mats, long established in earlier periods, adapted to fluctuating salinity and sedimentation rates within tidal zones. While animals had not yet appeared, the marine biosphere exhibited increasing heterogeneity in both form and function. Geological records from later fragments of Rodinia preserve thick sequences of shallow marine sediment, interbedded with evidence of changing water depths. These deposits hint at transgressions and regressions of the sea across continental margins, likely driven by tectonic subsidence and shifts in global sea level. Each advance of water over land created new habitat, and each retreat reshaped coastlines, reorganizing communities in its wake. As breakup progressed, the supercontinent's once singular edge transformed into a complex network of shores. The planet's surface geometry became more intricate, and with that intricacy came ecological consequences. Nutrients flowed more widely, habitats diversified, and marine life responded in quiet but significant ways. Changing coastlines thus marked more than a geographic adjustment. They represented a broadening of environmental possibility, a gradual enrichment of the interfaces between rock and water. In the shifting contours of these new seas, the biological world found space to expand its variations, setting the stage for further transformation in chapters yet to unfold. Long after mountains have worn down and seas have shifted, stone continues to carry memory. The landscapes of Rodinia no longer stand as they once did, yet their history endures in minerals formed under pressure, heat, and time. To understand this distant era, geologists do not rely on visible outlines, but on chemical and physical signatures locked within ancient rock. These records are subtle, yet they remain remarkably durable across billions of years. Among the most valuable witnesses are zircon crystals. These small, resilient minerals form in cooling magma and incorporate trace amounts of uranium into their structure while excluding lead. Because uranium decays into lead at a predictable rate, the ratio between parent and daughter isotopes becomes a reliable clock. By measuring these ratios with precise instruments, scientists determine when the crystal crystallized from molten rock. Zircon grains eroded from long vanished mountain belts may be transported into younger sediments, carrying within them timestamps that reveal the age of continental assembly and breakup. Isotope ratios extend beyond dating. Elements such as oxygen, carbon, and strontium exist in multiple isotopic forms, and their relative abundances shift in response to environmental conditions. Oxygen isotopes preserved in minerals can indicate temperatures at the time of formation or reveal interactions with ancient seawater. Carbon isotopic signatures recorded in sedimentary rocks reflect fluctuations in the global carbon cycle, tracing intervals when organic carbon burial or volcanic outgassing altered atmospheric composition. Through these measurements, Scientists reconstruct aspects of climate and ocean chemistry that left no visible fossils. Iron formations and sulfur isotopes also contribute to this narrative. Variations in sulfur isotopic ratios provide insight into atmospheric oxygen levels and the presence of microbial metabolisms that cycle sulfur compounds. Subtle anomalies in these ratios help identify transitions between more oxygen rich and more reducing conditions in the oceans. In this way, chemistry replaces bone as the primary storyteller for an age before animals. Magnetic signatures preserved in rocks add a spatial dimension to the record. When lava cools, iron-bearing minerals align with Earth's magnetic field, effectively freezing in a snapshot of magnetic orientation. Sedimentary rocks can also acquire magnetic remnants during formation. By analyzing these signals, geologists determine the latitude at which a rock formed. When applied across multiple continents, paleomagnetism allows reconstruction of Rodinia's configuration, revealing which landmasses were connected and how they drifted apart through time. These methods require careful correction and cross-validation. Rocks may undergo metamorphism or chemical alteration, potentially resetting or modifying original signals. Scientists compare results from different isotopic systems, examine microscopic structures within minerals, and integrate structural geology with geochemical data. Through this layered approach, they build a coherent reconstruction from fragments dispersed across modern continents. Even sedimentary layering holds clues. Rhythmic deposits tied to tidal or climatic cycles offer information about Earth's rotation and environmental variability. Trace element concentrations indicate sources of sediment and the intensity of weathering in distant mountain belts. Each dataset contributes a small piece to a wider mosaic. The reconstruction of Rodinia, therefore, emerges not from a single discovery, but from the convergence of independent lines of evidence. Zircon crystals date events of formation and metamorphism. Isotope ratios chart atmospheric and oceanic chemistry. Magnetic orientations map the shifting positions of continents. Together, these chemical signals enable scientists to peer beyond erosion and tectonic reworking into a time when land, sea, and sky were arranged in unfamiliar ways. Ancient rocks do not speak in dramatic tones. They whisper through numbers and ratios, through aligned minerals and preserved inclusions. Yet within those whispers lies a detailed chronicle of a world long transformed, patiently recorded in the enduring language of chemistry and magnetism. Change rarely announces itself with a single event. More often, it gathers through accumulation, subtle adjustments layered one upon another until the overall pattern shifts. As Rodinia continued to fragment and new ocean basins widened, environmental conditions began to reorganize in ways that would slowly favor increased biological complexity. The supercontinent's breakup altered circulation, nutrient distribution, and the balance of gases in the atmosphere and ocean, setting in motion trends that extended far beyond the lifespan of any single landmass configuration. The multiplication of coastlines created expanded continental shelves bathed in sunlight. These shallow marine environments provided broad platforms for photosynthetic organisms and for early eukaryotic life forms already experimenting with cellular specialization. At the same time, tectonic activity and continued weathering delivered nutrients into the ocean at renewed rates. Phosphorus, iron, and trace elements moved through rivers into marginal seas, stimulating productivity that, over long durations, influenced global biogeochemical cycles. One of the most consequential trends during this era was the gradual rise of atmospheric oxygen. Cyanobacteria had been releasing oxygen for hundreds of millions of years, yet the concentration of free oxygen in air and surface waters did not climb steadily without interruption. Burial of organic carbon in marine sediments played a central role. When photosynthetic organisms fix carbon dioxide into organic matter, and a portion of that material is buried rather than oxidized, oxygen accumulates as a residual product. Tectonic adjustments and expanding shelf areas may have enhanced the efficiency of this burial, allowing oxygen levels to climb incrementally. This increase did not happen abruptly. Instead, it unfolded across millions of years, punctuated by fluctuations. Nonetheless, rising oxygen altered the redox state of the oceans, influencing the solubility of metals and the distribution of nutrients. More oxygenated surface waters supported metabolic strategies requiring higher energy throughput. The energetic cost of building larger, more organized bodies could be met only when sufficient oxygen was available to fuel respiration. Genetic potential also matured during this interval. Regulatory networks governing cell differentiation, adhesion, and communication expanded within eukaryotic lineages. Molecular innovations, such as collagen proteins and components of developmental signaling pathways, emerged through duplication and modification of existing genes. These capabilities did not immediately yield animals, but they laid the molecular groundwork necessary for multicellular organization beyond simple algal forms. Environmental shifts associated with Rodinia's breakup likely introduced gradients and variability that encouraged diversification. Alternating phases of glaciation and deglaciation, reorganized ocean currents, and fluctuating nutrient regimes created selective pressures favoring adaptability. Organisms able to exploit transient conditions would have gained advantage, gradually enriching the repertoire of biological forms present in the oceans. By the time fully complex animals began to appear in the fossil record during the Ediacaran period, the foundations had been prepared across hundreds of millions of years. Oxygen concentrations had risen to thresholds supportive of larger body sizes. Continental configurations had diversified coastlines and marine habitats. Biochemical cycles had stabilized within ranges conducive to sustained complexity. Rodinia, therefore, occupies a transitional place in Earth's long narrative. It was neither the origin of life nor the moment when animals first flourished. Instead, it served as a prelude, a stage during which tectonic, chemical, and biological processes converged to create conditions that made later innovation possible. Its assembly shaped climates and carbon cycles. Its fragmentation reshaped oceans and coastlines. Its environmental legacy influenced the trajectory of evolving life. In this sense, the supercontinent represents not an endpoint, but a hinge. The world that followed would carry forward its geologic rearrangements while building upon the metabolic and genetic advances incubated during its tenure. Out of shifting shores and rising oxygen emerged a planet increasingly prepared for forms that would move, sense, and eventually transform the land itself. When later ages assembled their own vast continents, the pattern was not entirely new. Pangaea, which gathered much of Earth's land during the late Paleozoic and early Mesozoic, followed the same fundamental rhythm of convergence that had shaped Rodinia long before. Plates collided, oceans closed, mountain belts rose, and a single immense landmass once again dominated global geography. In structure and tectonic logic, the two supercontinents shared a common architecture. Both formed through the slow welding of drifting crustal fragments. Both created expansive interiors, distant from moderating seas. Both altered ocean circulation and atmospheric patterns on a planetary scale. Yet beneath these structural similarities lay profound biological differences. By the time Pangaea assembled, Earth had already undergone the Cambrian diversification and the long evolution of marine ecosystems. Forests covered large portions of land, rooting deeply into soil and stabilizing slopes. Amphibians and reptiles moved across floodplains. Insects filled the air. Complex food webs linked terrestrial and marine realms in intricate exchanges of energy and matter. The supercontinent of that era was geologically grand, but biologically crowded. Rodinia, in contrast, rose into existence before animals had taken hold and long before forests transformed the continents. Its terrains were shaped primarily by rock, water, and wind, rather than by the constant modification imposed by roots, burrows, and grazing. Microbial life flourished in oceans and along coastal margins, yet the land remained largely unoccupied by visible organisms. The absence of complex terrestrial ecosystems gave Rodinia a starkness that Pangaea never knew. Where Pangaea's interiors hosted seasonal monsoons interacting with vegetation and soils rich in organic matter, Rodinia's vast expanses reflected a simpler interplay between atmosphere and lithosphere. Climate patterns in both supercontinents bore certain parallels. Massive interiors fostered arid conditions in regions removed from oceanic moisture. Mountain ranges generated rain shadows and influenced atmospheric circulation. Continental assembly intensified weathering of uplifted rock, affecting the carbon cycle and long-term temperature regulation. In each case, tectonic configuration is fed back into the climate through chemical and physical pathways. Yet the outcomes diverged in detail. Pangaea's vegetated landscapes contributed actively to carbon sequestration and atmospheric composition. Forests enhanced chemical weathering, increased soil development, and modulated regional humidity through transpiration. These biological processes intertwined with tectonic forces, producing a climate system in which life was a significant agent of change. Rodinia's climate, by comparison, operated with far less biological intervention on land. Weathering occurred without root networks, carbon storage in soils remained minimal, and the atmosphere responded more directly to volcanic outgassing and inorganic reactions. Ocean circulation differed as well. During Pangaea's time, marine ecosystems were populated by diverse animals, from corals to marine reptiles, interacting within complex trophic structures. Coastal productivity supported fisheries that would later fossilize into limestone and shale sequences rich with recognizable remains. Rodinia's seas, while biologically active at microbial and early eukaryotic levels, lacked such visible complexity. Nutrient cycles operated efficiently, yet without the cascading interactions associated with large, mobile organisms. The comparison highlights not merely geological repetition but evolutionary progression. Earth builds supercontinents as part of its tectonic cycle, yet the biological context in which each forms is never identical. Rodinia assembled during a stage when the biosphere was still largely confined to microscopic realms and simple multicellular experiments. Pangaea arose in a world already transformed by hundreds of millions of years of evolutionary innovation. In this contrast, Rodinia appears more barren, not because it lacked dynamic processes, but because complexity had not yet extended across land. Its silence and starkness reflect timing within Earth's long unfolding narrative. Both supercontinents reshaped climate and geography, yet only one carried forests and animals across its plains. The other stands as an earlier chapter, a structural precursor to later gatherings of land, formed before life had fully diversified into the forms that now define familiarity. Light itself was different in that distant age, though the difference would not have been visible in a single glance. The sun, powered by steady fusion within its core, has not burned at a constant intensity across Earth's history. Stellar evolution follows gradual rules. As hydrogen converts into helium, the internal structure adjusts, causing luminosity to rise slowly over billions of years. During Rodinia's time, solar output was measurably lower than it is today, part of a long arc of brightening that continues even now. This quieter radiance presents an intriguing tension within the geological record. If the sun shone with less intensity, basic physics suggests that Earth should have been colder, perhaps cold enough to maintain permanent global ice. Yet evidence indicates that liquid oceans persisted across much of the planet, and sedimentary rocks formed in environments incompatible with perpetual freezing. This contrast between expected chill and observed warmth is often described as the faint young sun paradox, a reminder that planetary climate depends on more than incoming sunlight alone. The resolution lies in atmosphere and chemistry. Greenhouse gases absorb outgoing infrared radiation, trapping heat near the surface. Carbon dioxide, methane, and water vapor are central to this process. In early and middle Proterozoic times, carbon dioxide concentrations were likely higher than modern values, partly due to sustained volcanic outgassing and differing rates of weathering. Methane, produced by microbial metabolisms in low oxygen environments, may also have contributed additional warming. Together, these gases could compensate for reduced solar luminosity, maintaining surface temperatures above freezing across large regions. The balance was delicate. Too little greenhouse forcing and ice could expand dramatically. Too much, and temperatures might climb beyond stable thresholds. Throughout Rodinia's tenure, this interplay unfolded alongside tectonic reorganization and biological evolution. When uplift accelerated chemical weathering, carbon dioxide was drawn down, nudging the climate toward cooling. When volcanic provinces released gases into the atmosphere, warming tendencies strengthened. Against this shifting background, the sun continued its incremental brightening, adding a slow upward pressure on baseline energy input. Ocean chemistry also mediated warmth. Water absorbs and redistributes heat efficiently, smoothing regional contrasts and buffering rapid changes. Darker ocean surfaces absorb more sunlight than reflective ice or bare rock, enhancing warming in open water areas. During intervals when ice retreated, lower albedo would amplify the energy retained by the planet, helping to counteract the sun's diminished luminosity. Cloud cover introduces further nuance. Clouds can reflect sunlight back into space, reducing surface heating, but they can also trap infrared radiation. The net effect depends on altitude, composition, and global distribution. In a world with different atmospheric chemistry and continental arrangement, cloud dynamics likely differed from modern patterns, influencing climate sensitivity in ways still studied through modeling. Over immense spans of time, solar evolution gradually altered the stage upon which these interactions played out. As luminosity increased, the threshold for maintaining liquid water became easier to achieve, even if greenhouse gas concentrations declined. This slow brightening has implications that extend beyond Rodinia, shaping climate potential across all of Earth's chapters. The younger sun, therefore, forms part of a larger equilibrium. Its subdued brilliance did not dictate an icy planet, because atmospheric composition and geological processes adjusted in tandem. Climate emerged from a synthesis of stellar physics, volcanic emissions, weathering feedbacks, ocean circulation, and biological activity. Even under a fainter star, Earth remained capable of sustaining liquid seas and nurturing incremental biological innovation. In that balance between celestial energy and planetary response, Rodinia unfolded beneath a sun still gaining strength. The light was softer than today, yet sufficient, filtered through gases and clouds, to maintain a world neither frozen nor overheated, but poised within a narrow band of habitability that would endure through further transformation. Before complex life altered the atmosphere with calls, wings, and movement, the planet spoke in simpler tones. Sound still traveled across its surface, carried by air and water, shaped by stone and sky. Yet the sources of that sound were almost entirely physical. Rodinia's world was not silent, but its voice belonged to elements rather than to animals. The wind moved first. Across wide plateaus and open expanses of rock, air currents flowed without interruption from forest canopies or grasslands. There were no leaves to tremble, no branches to creak, no insect wings to hum in layered harmony. Instead, wind skimmed directly over exposed ground, sweeping across dunes or scraping along ridges formed during continental collision. The tone would have been low and continuous, a steady rush shaped only by terrain and temperature gradients. Water added a second register. Waves broke against empty shores, their rhythms set by tides and distant storms. Along young coastlines formed during fragmentation, surf echoed against newly carved cliffs. In shallow seas, currents shifted sediments in soft, granular motions, whispering beneath the surface. Rivers flowed where rain collected, cutting channels through bare rock and depositing silt in coastal basins. Without roots to stabilize banks, channels likely shifted course more readily, creating brief surges and collapses that punctuated the larger acoustic background. Thunder completed the atmospheric cadence. Convection within the air mass still produced storms, especially along warm coastal margins. Lightning flashed across skies that had never yet heard the beating of wings. Thunder rolled unhindered over plains and across mountain belts, reverberating without being absorbed by dense vegetation. Each storm would pass, leaving once again the steadier undertones of wind and surf. From deeper below came intermittent volcanic rumbling. As mantle heat accumulated and rifts widened, magma forced its way toward the surface. Eruptions would have cracked open quiet horizons with explosive releases of gas and molten rock. The sound of such activity is not constant but episodic, a reminder that even in apparent stillness, tectonic forces remain active. Lava, spreading across the ground, carries its own subdued roar, followed by the cooling hiss as molten material meets air or water. What is absent in this soundscape is as important as what remains. There were no choruses of birds at dawn, no rustling of mammals in undergrowth, no buzzing insects weaving through warm air. Biological noise today fills subtle spaces between elemental sounds, creating layered textures that mask underlying currents. In Rodinia's age, those spaces were open. The atmosphere transmitted primarily geophysical vibration, uninterrupted by communication between mobile organisms. This absence would have altered the perception of space. Without sudden calls or patterned rhythms produced by life, distance might have felt more expansive. A gust of wind or distant thunder would travel without meeting overlapping layers of animal sound. The acoustic horizon would extend farther, with fewer interruptions to modulate its continuity. Sound interacts with landscape, and landscape in this era responded without mediation by ecosystems. Mountain slopes reflected gusts and echoes. Coastlines shaped the crash of waves. Rift valleys funneled wind into focused streams. The planet's auditory identity derived from terrain and climate alone. Such quiet does not imply emptiness of process. Chemical cycles operated, microbial life flourished in water and sediment, tectonic plates shifted beneath the crust. Yet, these activities unfolded without the audible signals that later accompanied complex organisms. Rodinia's voice belonged to air, water, stone, and fire, layered into a restrained composition that emphasized elemental forces over biological expression. In that measured interplay of wind, surf, thunder, and volcanic murmur, the world maintained a steady tone. It was a planetary quiet not defined by total silence, but by the absence of animated reply, a soundscape shaped almost entirely by physics and the enduring pulse of the earth itself. Long before forests exhaled their seasonal fragrance and soil released the scent of decay, the chemistry of the air carried a different character. Odor is the imprint of molecules moving invisibly through the atmosphere, and in Rodinia's era those molecules followed a composition unlike the one familiar today. Oxygen was present, yet its concentration remained lower than modern levels. Carbon dioxide likely occupied a more prominent share, joined at intervals by gases rising from volcanic provinces and rifting margins. The air would have been breathable only in a biochemical sense for microorganisms, but its qualitative scent would have diverged from that of a world shaped by plants and animals. Lower oxygen alters not only combustion and metabolism, but also atmospheric chemistry. With fewer oxidative reactions occurring in the open air, certain gases persist longer. Methane, generated by microbial communities in low oxygen environments, could accumulate before being broken down by photochemical processes. Methane itself has little smell at the concentrations expected, yet its presence reflects an atmosphere less dominated by rapid oxidation. In such conditions, trace sulfur compounds and other reduced gases might travel farther before dispersing. Carbon dioxide at elevated levels contributes no direct scent perceptible to human senses, yet its abundance shapes the overall mixture. The balance between carbon dioxide and nitrogen influences air density and the thermal properties of the lower atmosphere. Combined with differing trace gases, this mixture would have created an environment chemically stable, yet distinct in subtle ways. Volcanic emissions introduced sharper notes. Sulfur dioxide, hydrogen sulfide, and halogen-bearing compounds escape during eruptions and through persistent degassing from tectonically active regions. Hydrogen sulfide, recognizable today by a characteristic rotten egg odor, can arise from both volcanic vents and anoxic waters. In areas where rifting thinned the crust, fumaroles may have released faint but persistent plumes. These localized sources could temporarily dominate the atmosphere's character near active margins. Ocean chemistry interacted continuously with air above it. Surface waters exchange gases with the atmosphere through diffusion and wind-driven mixing. During intervals when deep waters carried reduced compounds upward, sulfur-bearing gases might have entered the air in greater quantities. Iron-rich waters, if exposed to oxygen at the surface, would precipitate iron oxides rather than release strong odors. Yet associated microbial metabolisms could influence trace gas production. The interface between sea and sky acted as a chemical membrane, moderating concentrations through solubility and biological activity. Without extensive terrestrial vegetation, there were no volatile organic compounds emitted from leaves and bark to perfume the atmosphere. Modern forests release a complex array of molecules that contribute to the fresh scent, often associated with living landscapes. In Rodinia's time, the absence of such emissions removed an entire dimension of airborne chemistry. Instead, the prevailing aroma would have been shaped by mineral surfaces heated by sunlight, saline spray from coastal waters, and intermittent injections of volcanic gases. Rain interacting with exposed rock may have produced subtle mineral odors, similar to the scent sometimes detected when storms strike dry stone. Yet, lacking soil rich in organic matter, that scent would not have been accompanied by the earthy undertones common in present ecosystems. Atmospheric composition thus reflected predominantly inorganic processes, moderated by microbial exchanges largely confined to water and sediment. The smell of the air, if perceived by senses adapted to modern conditions, would have seemed thinner in oxygen, yet occasionally tinged with sulfur near active zones. Across most regions, however, it likely bore only the faint saline and mineral hints of ocean spray and sun-warmed rock. Chemistry, rather than biology, defined its character, a quiet atmospheric signature aligned with a planet still evolving toward greater complexity. From a vantage point far above the atmosphere, the planet would have appeared arranged with a clarity rarely seen in later eras. Instead of continents scattered like drifting fragments, there stretched a single dominant landmass occupying much of one hemisphere. Rodinia's outline, though irregular along its edges, read as a unified form against the dark sweep of ocean. From orbit, the geometry alone would signal a world in a distinct tectonic phase, gathered rather than dispersed. The coastline traced an immense boundary between rock and water, curving across thousands of kilometers without interruption by separate continental clusters. Shallow embayments and rifted margins would appear as gentle scallops along its perimeter, yet the overall impression remained one of continuity. Tidal patterns would wrap around a singular edge rather than weaving among multiple landmasses. Ocean currents, guided by this configuration, would circulate differently than in the fragmented geography familiar today. Color, too, would communicate differences. Modern Earth is textured by green expanses of forest, tan deserts stabilized by vegetation, white polar ice, and the patchwork of seasonal change. In Rodinia's time, the palette would have been more restrained. Exposed rock and mineral surfaces reflect shades of muted brown, gray, and rust. Without widespread plant cover, no deep green would soften the continental interior. Coastal waters might display lighter tones where sediments entered shallow seas, yet the land itself would lack the mottled variation created by biomes. Ice, during colder intervals, could overlay significant portions of the surface with pale brightness. Glacial sheets and seasonal snow would extend reflective patches across parts of the supercontinent, intensifying contrasts between white expanses and darker rock. At other times, the absence of extensive ice would reveal a primarily mineral landscape, its coloration shaped by lithology rather than by biological growth. Cloud systems would swirl above, driven by temperature gradients between ocean and interior. From orbit, these formations might dominate visual perception, masking and revealing the surface beneath. The pattern of storm tracks would differ from that of a modern configuration, influenced by the single large mass-altering heat distribution. Monsoonal circulations near coastal margins could appear as seasonal belts of cloud, while interiors might remain clearer due to arid conditions. The oceans, occupying a vast portion of the globe, would retain their deep blue under sunlight, though their configuration around a unified landmass would change current pathways. Without narrow straits dividing continents, major gyres would reorganize, shaping thermal contrasts visible in satellite-like perspective. Sediment plumes from rivers draining uplifted terrains would create lighter arcs extending into shallow basins, hinting at dynamic exchange between land and sea. Seen from such altitude, Earth might appear simpler in structural terms, its components fewer and more consolidated. There would be less fragmentation, fewer boundaries between distinct continental units. Yet simplicity of outline does not imply absence of complexity within. Beneath the visible surface, tectonic stresses would persist, oceans would circulate through layered currents, and microbial life would animate waters invisible from afar. The view from orbit would emphasize pattern over detail. A single massive landform bordered by continuous shorelines, subdued in color yet animated by shifting cloud shadows and reflective ice, would convey a planet in a different chapter of its tectonic cycle. Without forests to paint its continents green, or sprawling animal-driven ecosystems to texture its margins, Rodinia's Earth would present a more austere visage from space, defined primarily by geology and ocean, awaiting future transformations that would gradually diversify its appearance. No supercontinent stands alone in Earth's history. Rodinia, immense though it was, belonged to a longer procession of gatherings and dispersals that stretched backward and forward across deep time. Before it, other landmasses had collided into earlier configurations, their names now preserved in fragments of crust and mineral memory. After it, new arrangements would rise from the slow choreography of plates. The surface never settles permanently into any one form. Tectonic motion arises from convection within the mantle, where heat from Earth's interior drives gradual circulation of solid rock behaving over long durations like a viscous fluid. Where currents ascend, lithosphere thins and rifts. Where they descend, oceanic crust bends into subduction zones, pulling attached plates inward. Through this continuous redistribution of mass and energy, continents wander across the globe. At times they converge into consolidated assemblies, at others they separate, opening fresh ocean basins between them. Rodinia was neither the first nor the final expression of this rhythm. Prior supercontinents, such as Columbia, assembled in earlier eons under similar forces of convergence. Though much of their surface expression has been erased by erosion and metamorphism, isotopic signatures and structural alignments reveal their former unity. These predecessors demonstrate that continental aggregation is not an anomaly but a recurring phase within a grand tectonic cycle. The reasons for repetition lie partly in physics. As continents cluster, they insulate the mantle beneath them, slowing heat loss to space. Thermal energy accumulates below the thickened lithosphere, promoting uplift and eventual fracturing. Over immense spans of time, this internal heating destabilizes the very configuration it helped sustain. Rifting begins, continents fragment, and dispersal redistributes thermal gradients across the globe. In this way, assembly carries within it the conditions for breakup. Climate interacts with this cycle as well. The arrangement of land and sea influences ocean currents, atmospheric circulation, and chemical weathering. When continents occupy polar positions, ice sheets may expand more readily. When land spans equatorial regions, weathering rates shift and carbon dioxide levels respond. Each supercontinental phase shapes global climate patterns, which in turn affect erosion and sedimentation, subtly feeding back into tectonic and geochemical systems. From a biological perspective, each configuration creates distinct opportunities and constraints. The supercontinent that formed long after Rodinia, Pangaea, witnessed forests spreading across wide plains and animals diversifying in varied environments. Earlier assemblies existed before such complexity. Future arrangements, still hundreds of millions of years ahead, will host life forms and climates that cannot yet be predicted with precision. The tectonic cycle does not prescribe biology, but it frames the environments within which evolution unfolds. The long arc of supercontinents can be traced through zircon ages, paleomagnetic reconstructions, and the geometry of mountain belts that once lay contiguous before later separation. These clues reveal a tempo measured in hundreds of millions of years, far slower than seasonal cycles or even evolutionary radiations. Continents drift at rates comparable to fingernail growth, yet, given sufficient time, they reorganize the face of the planet entirely. Rodinia occupies one movement within this extended composition. Its assembly marked a convergence of earlier fragments. Its fragmentation prepared the stage for new oceans and later gatherings. Earth's surface reshapes itself through repetition, not in identical patterns, but in recurring phases of clustering and dispersal. The rhythm of tectonic time is steady, though nearly imperceptible within a single lifetime. Over spans that dwarf human history, continents merge, rest, and separate again. In that enduring cadence, Rodinia stands as one verse among many, part of a cycle that began long before and will continue long after its outlines have faded into the shifting mosaic of crust. Strangeness does not always arise from violence or chaos. Sometimes it emerges from absence. The world shaped during Rodinia's time feels alien not because it defied physical laws, but because so many features now taken for granted had not yet appeared. The outlines of continents existed. Oceans rose and fell with tides. Storms moved across the sky. Yet the visible imprint of life on land remained almost entirely missing. Terrain, stretched unbroken by trunks or stems, uninterrupted by movement, patterned only by erosion and tectonic uplift. Modern landscapes are inseparable from biology. Roots fracture stone, stabilize slopes, and draw minerals upward, leave slow rainfall and moderate temperature near the ground. Animals burrow, graze, and transport nutrients across ecosystems, constantly reshaping soil and sediment. In Rodinia's era, these interactions had not yet taken hold. Landforms evolved primarily through wind, water, and gravity, guided by mechanical and chemical forces rather than by living mediation. The contours of valleys and ridges reflected geological processes operating with minimal biological interference. Ecosystems, where they existed, were concentrated largely in the oceans. Even there, complexity remained modest compared to later ages. Microbial communities and early eukaryotes participated in nutrient cycles, yet food webs lacked the layered trophic structures that animals would later introduce. Without predators roaming shorelines or herbivores grazing shallow seas, ecological interactions were simpler in structure. Energy flowed through photosynthetic and chemosynthetic pathways, then back into sediment and water without the amplification created by mobile consumers. This simplicity altered planetary dynamics. Today, vast forests influence atmospheric chemistry through photosynthesis and respiration on continental scales. Soil microbes regulate carbon storage across entire biomes. Marine plankton contribute to cloud formation by emitting trace gases. In Rodinia's time, such feedbacks existed primarily in microbial form, operating at smaller spatial scales and with less structural diversity. The balance between atmosphere, ocean, and crust depended more directly on tectonic emissions and inorganic weathering. The dominance of geology in shaping surface character lends this era an austere quality. Mountain belts rose and eroded without being anchored by root systems. Rivers transported sediment across exposed floodplains without encountering vegetation that would later stabilize channels. Shorelines shifted according to sea level and subsidence, unbuffered by coral reefs or mangrove-like communities. The rhythm of change followed tectonic pulses and climatic oscillations rather than ecological succession. Color, texture, and sound all reflected this imbalance. Without broad swaths of vegetation, continental interiors displayed the hues of mineral composition. Without complex animal communities, terrestrial acoustics remained confined to elemental forces. Even atmospheric composition bore the imprint of rock and microbe more than of forest canopy or grassland transpiration. Biology was present, persistent, and evolving, yet its reach across land was still limited. To consider this world is to encounter a planet governed primarily by lithosphere and ocean, with biosphere acting in narrower domains. The systems were interlinked, yet the scale of biological influence was restrained compared to later chapters. Earth felt alien because its familiar green mantle had not yet emerged, and because movement across land had not yet diversified into visible, patterned life. This era reveals that habitability does not require the landscapes now associated with life. Oceans remained active, chemistry complex, tectonics vigorous, yet the surface impression was one of elemental predominance. Rock, water, and air defined the scene more fully than organisms. In that geological clarity, Rodinia stands apart, a reminder that Earth has passed through phases when living systems had not yet assumed their later prominence, and when the planet's face was sculpted chiefly by the steady persistence of stone. Understanding a world so distant in time requires patience with fragments. No single outcrop reveals Rodinia entirely. No fossil preserves its full horizon. Instead, knowledge accumulates from pieces scattered across continents that once lay joined. Geologists read those pieces the way historians read weathered documents, extracting age, orientation, and environmental context from materials that have endured compression, metamorphism, and drift. Rock dating provides the temporal scaffold. Zircon crystals, resilient and chemically stable, record the moment they crystallized from molten material. Uranium within them decays into lead at known rates, allowing ages to be calculated with precision measured in millions of years. By dating igneous intrusions, metamorphic overprints, and detrital grains embedded in sediments, scientists constrain when continents collided, when mountain belts formed, and when rifting initiated. These numerical anchors define the broad span during which Rodinia assembled and later fragmented. Paleomagnetism adds spatial reconstruction. As molten rock cools, magnetic minerals align with Earth's field at that moment, preserving a directional imprint. Sedimentary rocks can also lock in magnetic orientations as particles settle through water. By measuring these signatures, researchers infer the latitude at which rocks formed. When similar aged rocks on separate continents share compatible magnetic histories, they suggest prior connection. By comparing magnetic datasets across many regions, scientists gradually assemble paleogeographic maps that position ancient landmasses relative to one another. Sedimentology provides environmental detail. Grain size, layering patterns, and mineral composition reveal whether a deposit formed in deep ocean, shallow shelf, river channel, or glacial setting. Striated clasts and dropstones indicate ice transport. Ripple marks and cross-bedding suggest current flow. Evaporite minerals signal arid basins. Through careful interpretation, sedimentary sequences disclose climate fluctuations and shoreline movements during Rodinia's tenure. These clues are subtle yet cumulative, building context for larger tectonic patterns. Fossilized microbes, though microscopic, offer additional insight. Stromatolites, layered structures created by microbial mats, record photosynthetic activity in shallow marine environments. Microfossils, preserved within cherts, document the presence of early eukaryotes and bacterial communities. Isotopic signatures associated with organic matter indicate metabolic pathways active in ancient seas. While no towering skeletons mark this era, these small remains confirm that life persisted and adapted within shifting environmental conditions. Geochemical analyses further refine the picture. Ratios of carbon, sulfur, and strontium isotopes trace changes in atmospheric composition and ocean chemistry. Trace elements signal degrees of oxygenation in marine waters. By integrating these datasets with tectonic reconstructions, scientists test hypotheses about climate dynamics, supercontinent assembly, and biological evolution. Models are constructed, compared against new measurements, and revised as additional evidence emerges. Uncertainty remains an inherent part of the reconstruction. Metamorphism can overprint earlier signals. Erosion removes portions of the record entirely. Paleomagnetic data can be altered by later heating events, requiring careful screening. The precise configuration of Rodinia's margins is still debated, as different datasets permit slightly different arrangements. Climate interpretations depend on assumptions about greenhouse gas concentrations and feedback strengths that cannot be observed directly. Yet, scientific understanding does not rest on a single line of evidence. It arises from convergence. When independent methods align in chronology, geography, and environmental inference, confidence increases. Where disagreements persist, they guide further investigation rather than halt progress. Through radiometric clocks, magnetic orientation, sedimentary textures, and microscopic fossils, the contours of this ancient world take shape. The portrait is not complete in every detail, but it is grounded in measurable properties preserved within stone. Each new analysis adjusts the frame slightly, refining rather than overturning the larger outline. What emerges is a reconstruction built incrementally, attentive to both data and doubt. Rodinia's existence and character are inferred not from imagination, but from persistent signals embedded in Earth's crust, interpreted through methods that continue to evolve as instruments grow more precise and models more nuanced. Long after its mountains softened and its coastlines dissolved into younger seas, Rodinia did not vanish. Its influence traveled forward in processes rather than in form, woven quietly into the mechanics of a planet still experimenting with itself. The arrangement of nearly all land into one immense body-altered circulation in ocean and atmosphere, adjusting currents and weathering patterns in ways that continued to echo even as the supercontinent began to separate. Climate does not reset when continents move. It carries memory in carbon, in ice, in the chemistry of water. The vast exposures of rock that once faced rain and wind increased the drawdown of atmospheric carbon dioxide through chemical weathering. Rivers carried dissolved minerals toward the ocean basins, where carbon became locked into sediments. Over spans measured in millions of years, such processes nudged the planet toward cooler states. These gradual adjustments helped prepare the conditions that would later allow ice to expand across wide latitudes. The great glaciations that followed were not isolated events. They grew from tectonic arrangements and feedback cycles already set in motion during Rodinia's tenure. Ocean chemistry, too, shifted under this configuration. As nutrients washed from eroding highlands into coastal waters, productivity fluctuated. Burial of organic carbon influenced oxygen levels in the atmosphere. Subtle variations in trace elements altered the redox balance of marine environments, encouraging some microbial metabolisms while constraining others. The seas that surrounded Rodinia were laboratories in which biological and geochemical systems interacted slowly, refining feedback loops that would shape later eras. When the supercontinent fractured, new coastlines emerged, and shallow seas spread across continental margins. These changes increased habitat diversity and circulation pathways, allowing oxygen to mix more efficiently through portions of the ocean. The gradual rise of atmospheric oxygen, already underway, gained momentum in a world where continents were no longer clustered into a single interior, far from the moderating influence of the sea. Complexity does not arise from a single cause. It requires an ensemble of conditions aligning across time. Rodinia's assembly and breakup contributed to that alignment. The emergence of complex multicellular life would come later, yet the groundwork formed here. Altered nutrient cycles, oxygenation events, and climatic oscillations acted together to expand ecological possibility. The planet that eventually supported animals and forests was not a sudden transformation, but a continuation of trends rooted in deeper time. Rodinia functioned less as a culmination and more as preparation, shaping boundaries within which future innovation could occur. Earth has assembled supercontinents before and would do so again. Each cycle rearranges coastlines, climates, and life's opportunities. Rodinia occupies one arc within this long rhythm, distinct yet connected to both predecessors and successors. The continents beneath modern forests and cities carry fragments of that ancient configuration, metamorphosed and fragmented, but not erased. Zircon crystals and magnetic signatures still preserve orientations from a sky long altered. The world visible today feels complex and vibrant, dense with biological interaction. Yet beneath soil and infrastructure lie rocks forged in a quieter biosphere when geology outweighed ecology in determining the planet's character. Rodinia's landscapes, though reshaped beyond recognition, persist in structural grain and mineral composition. They form basement foundations over which later chapters were written. This legacy is not dramatic, it is cumulative. Tectonic assembly shaped climate trajectories. Climate adjustments influenced chemistry. Chemistry constrained and enabled life. Through such linked sequences, a world that once felt unfinished became the groundwork for richness that followed. Earth is not fixed in any single expression. Across deep time, it reforms itself entirely, exchanging atmospheres, rearranging oceans, and repurposing continents. The planet we inhabit is one moment within that continuity, layered above the quiet remains of an earlier Earth that prepared the way without ever resembling what came after.